Yeah, it's going to be on all the North American servers.
Okay, guys, this week in lab we're doing double E2 elimination of your dibromide that you made several weeks ago. It's got two bromines, it's got two leaving groups. So, it's actually another James Bond twist. That's the next James Bond movie, double E2 elimination. Let's look at this last page of substitution handout. Question is right here. This is a SN2. There's actually two parts to it. First step is you got this carbon with a leaving group. And you've only got one carbon with a leaving group and you've only got one nucleophile. Here's a nucleophile, here's the carbon with the leaving group. Electrons attack here, maybe. I'm saying it's likely SN2, so I'm going to show an SN2, kick that off. That's a strong nucleophile, it's an sp3 nitrogen, it can do SN2. The purpose of the sodium carbonate is to deprotonate the H once it makes a bond. Xylene is a solvent, they sell that at Walmart, maybe Walmart, they sell it at Lowe's, I know. The next step removes this ester group from the nitrogen, but we don't really know that chemistry yet. But right here is where they did make the bond with the SN2, nitrogen replaced bromine. The H was lost to go neutral. Again, the base removed the H. Everybody see that reaction? What's going on there? Any questions about it? What does reflux mean? Reflux is a fancy word for boil. We'll be reflexing in lab this week using a reflux condenser. Condenser in your hood. Boil for 10 hours. I'm sure you've reflexed before. You ever reflux eggs at home? Boiled some eggs. Likely SN2. Likely. Not sure. How would we confirm that it's SN2?
Stereochemistry?
Chelsea?
The stereochemistry?
Okay, possibly. There's no stereochemistry given here. That is chiral, but it's apparently racemic. They're not showing any precise stereochemistry. But if this was R, and then this was S, we would know it was SN2. But if this was R and this became racemic, we would know it was SN1. What's another way we think it's probably SN2? We really can't tell from stereochemistry because there's no stereochemistry shown or given. What's another way?
We have a small KOH.
No, KOH is the second step. That takes place next year. The first step is the SN2. The second step removes the ester group over here. I thought you were going to say you have a strong nucleophile. Strong nucleophile is going to do what? SN2. Yeah? Well, how do you know that neutral nitrogen is really strong? Yeah. But that's just kind of what your instructor told you. How do you know it really is strong? I mean, it is neutral. Maybe it's not strong enough. What's another way you could tell? Kinetics. If it's SN2, if we double the rate of the nucleophile, what will happen to the rate of reaction? It should double because SN2 reaction rate is some type of constant times concentration of leaving group substrate times concentration of nucleophile. But what if we change the concentration of the nucleophile and the rate stays the same? That means it's SN1. So you can determine it by doing a kinetic study, changing the concentration of reactants, seeing if they affect the rate. You got to know your reaction rate constant, or not your reaction rate constant, but your reaction rate equation. Why does it matter? What if you're working for this company, I don't know, Bristol Myers Squibb, and they're making this drug, and you're getting a lousy yield on this? You might propose, well, let's double the amount of this, and maybe this will make it react more. Well, only if it's SN2. If it's SN1, you can double this all you want, and you're not going to change it a bit. And so if it's SN1 and you ask the company to spend $5,000 more on doubling that, when it's not going to do a thing, they might not like you spending $5,000 on it. They're going to ask you where you took organic chemistry. So that's a reason why it would matter. You don't want to double something when that thing has nothing to do with the rate determining step. This is why we need to understand kinetics if we want to assess reactions and be able to modify reactions and know what's going on. Make sense? Any questions about that and how to confirm? There's a variety of ways, but don't forget kinetics. There's another SN2 here. At this point, they have this nitrogen, and it comes in here and it does an SN2, and they make this bond here, kicking off the chlorine. There's actually 3 SN2. Where's the other one? It must, oh, down here. There's another SN2. Because at this point, now they have this OH out here. And I don't like the choice of base because it requires some discussion, but we got to make this a minus to make it a good nucleophile. Then it comes in here and it kicks off that chlorine. And that's how they get that bond made. They're using an alkoxide base. What base did we use to make O minuses? It really wasn't a base, it was a redox reaction. Not hydroxide. We said hydroxide was not strong enough to make it O minus of a regular alcohol. Anybody? Abdul? No, we want to make the sodium alkoxide. I'll leave that with you. Let's look at the elimination sheet. We did 2 possible mechanisms for elimination. Did we finish those up? Yeah. The E1, what was the first step of the E1? No, the first step of the E1 was what?
Ionization.
Ionization, right? It's the same as the first step of an SN1. Ionization. After the ionization, what happened in the E1?
You get rid of the
Beta.
Beta elimination in a fast step. The base takes the H. 2 steps. Ionization followed by fast beta elimination to put the double bond in. What did we do with E2? So E1 had a carbocation intermediate just like an SN1 has. What did we do with E2? Well, I'm sorry, we switched it. We did E2 up here, right? We switched that. What did E2 look like? Did we have any intermediate cation?
No.
No. It was all concerted. Base takes the H, electrons move in, leaving group gets kicked off. We had 3 arrows, all concerted to make alkene, plus leaving group minus, plus the protonated base. Is that right? That's where we left off. The E2 that we showed was only 1 step. There was no intermediate. So which step was the rate determining step? that step. At the end, I asked you, could you show another mechanism for getting to those products? We showed two mechanisms up here. Which mechanism is it? Which mechanism is this elimination, E1 or E2? It's E2. Why? You don't want to form a primary carbocation. What's another reason it's E2? E2 meaning bimolecular. The base / nucleophile is strong. That's a strong base / nucleophile. If you have a strong base / nucleophile, they're bullies. They're going to stick their nose in there and be involved in the rate determining step. The example reaction is a E2 elimination. Concerted beta elimination. Did anybody come up with a third way to show this process of forming these products? Well, what if we did this? What if the base took an H and just left these electrons here? That would give minus here plus protonated base. So there's the protonated base formed. Check. Now how would we get, this would be an intermediate here I'm proposing. How would we then get the final product? What do we need to do to get the final product? What arrow movement do we need to show?
Double bond to bromine.
How about these electrons just come in here and kick that off? And that would give, what does this arrow give? Pi bond being formed, leaving group kicked off. Pi bond formed, leaving group kicked off. Does everybody agree that this process gives those products? Is this process like the two we showed before? Or is it a third different? Let's see, the two we showed before, the E1 involved making a carbocation. Well, I see no carbocation here, so it's different from that. The E2 involved everything happening at the same time. Well, I don't see that here, so this looks like a third method, right? E3. This is the third method. E3?
Yeah.
Well, there's not E3 because there's only two substrates. It can only be bimolecular. There's not a third substrate. I'm not going to tell you what this is called, but we're not covering this mechanism right now. This is sometimes alluded to in organic 2. This is a third elimination mechanism. For us right now, don't do it. We are not ever going to form an anion. And after I erase this, I'm never going to show such again this semester. This would be a carbanion. E1 or E2, neither of them involve carbanions. Okay? Because ultimately, these H's are not acidic. You're not just going to pull one off and make carbanion. So don't do it for E1 or E2. But do be aware that this is a third way to show this. And later on, you may be introduced to another elimination mechanism that may look like this. This occurs when the CH has some acidity. Don't do this for E1 or E2. Does everybody understand what I was showing there? A third way that we want to understand that we're not doing, at least not yet this semester. Okay, E1, E2. Let's pick up here an alternative example. If you take this alkyl bromide and heat it with T-butanol, you can get this alkene plus HBr. Hopefully you see that it's an elimination reaction because this molecule has to eliminate HBr to form this. We eliminate it. We remove it from the molecule. You know 2 elimination mechanisms, not 3. Forget about that one for this semester. Is this E1 or E2? E2 is bimolecular. What does bimolecular require? A strong nucleophile. It also requires a strong base. Is this a strong? If you're doing elimination, you call this a base. Is that a strong base? No. Strong bases are just like strong nucleophiles. Anions or sp3 nitrogens. Is that an anion or sp3 nitrogen? Weak base. So what's the mechanism? E1. Or you can say no base. I mean, that's really hardly even a base. It could be just solvent. Certainly not a strong base, which is needed for SN2. E1. Now the question becomes, can you do E1 on such a carbon with a leaving group? Can you do E1 on a secondary carbon, Antonio? You can. Tertiary would be better. Secondary is okay. You don't want to do primary. You can do E1 here. So let's just set up to E1. E1 based on this consideration, E1 here. So what's the mechanism? What's the first step? Ionization. A little bit of heat to help the ionization. And we get this carbocation. That's going to be your rate determining step. And what do we do next to get final product? Plus what? Br minus? We got 2 H's here. There's only 1 H there now. What do we have to do? We got to remove an H, beta elimination fast step. That could remove it, or if we want to make HBr, this can remove it. Put the electrons in, make pi bond, and we get that there. Two things to point out here. This is trans product. We're going to look at this in more detail in just a minute. Why trans? It looks like this is cis here. I mean, right? If we just put that double bond in, this would be cis. Well, what do we know about conformations like this? This thing is like right here. Is it going to just stay like this, or is it going to rotate and do like this? We talked about this week 2 and 3, right? This is just a conformation. This thing's going to rotate to give that cation. That's just like we looked at during test 1, conformations. Which conformation is favored? If we had this, we would call this maybe a, if you had it, it would be eclipse and syn. This is going to be anti. Which is better, syn or anti? Anti. This could be favored. And so actually, that's favored, and you actually remove H here, and you get trans. That's why I showed trans. We'll talk about that on the next page. What did this do in the mechanism I showed? Nothing much. Just solvent. In fact, if that was not even there, you could do the same reaction. A lot of times you can just take such things and just heat them and they'll eliminate. Don't even need to have a solvent. And that would be called a decomposition. Heating this will make it decompose into this plus this. And that would be driven by entropy because one molecule is converting to two. Show the rate equation for this mechanism. Type of constant that's inherent for the reaction. Times what? Times the alkyl bromide times what? Times nothing else. That's it. Rate determining step is just ionization of the alkyl bromide. That's it. E1. Okay, when regioisomers are possible, first thing we have to do is, well, are regioisomers possible? If we do a beta elimination here, there's only one possible product. Well, here's the alpha carbon, that's the carbon the leaving group is on. Here are beta hydrogens. I mean, there's only one type of beta hydrogen. We remove an H, electrons end up here, pi bond, leaving group gone. Pi bond's here. There's nowhere else to put pi bond because there's no other type of beta hydrogen present. You'll see down here that you have two types. I'll go ahead and show you. You have beta hydrogens here, so you can remove HCl and put double bond in over here. Or you have beta hydrogens here, and so you can put double bond over there. But up here you can only put it in right there. So there it is. And, so this is the only regioisomer possible from elimination. But it's also the only stereoisomer because this alkene does not have E or Z stereoisomers. So if you're asked to eliminate here, that's the only product you can show. There's no variation there. But if you're asked to beta eliminate from this substrate, you could eliminate over there and get that product. But you can also eliminate over here to get this product. And these would be regioisomers. But this end has a stereoisomer because it could be E or Z. So if you're asked to beta eliminate here, there's actually 3 possible products to show. At least theoretically. We need to determine which is going to be favored there. Which will be formed. It depends on a variety of factors, including mechanism. Well, is it E1 or E2? Base, stronger weak. We'll also look at, well, is it sterically hindered base? Also, the orientation of groups in the starting material. And we'll have to explain that when we look at it. So, that should be straightforward. Let's talk about the different things in making this choice. The first thing we want to talk about is, or we can say this, it's a statement. The most substituted alkene is the thermodynamic product. But we knew that, right? if you're looking at two alkenes that are isomers, isn't the one that's most substituted the more stable product? We've said that multiple times. The more stable or thermodynamic product, yes. When you're doing elimination, the most substituted alkene is called the Zaitsev product. Somebody's name. And Zaitsev is spelled about 8 different ways. Some books spell it with a Z. Zaitsev. It's Russian. It got translated to English, and everybody forgot how to spell it. The most substituted alkene is always the major product in an E1 elimination. There you go. Do we need to repeat that? That's the take-home message right there. If you're doing an E1 elimination, the Zaitsev product is always the favorite product. The Zaitsev product is your thermodynamic product. The thermodynamic product is your most substituted alkene. When you're doing an E1, it's easy. So, if this up here was E1, which product would be formed? First, second, or third? Well, it could be E1, right? I was about to say it couldn't be. It could be E1. Which product would be the E1 product? Would it be the first one? No, that's not the most substituted alkene. Would it be that one? Well, that's di-substituted. But hold on, that's also di-substituted. But we're looking for the most stable. Because most substituted, we could also tell, yes, they're both di-substituted, but which one's most stable? E. Is E more stable than Z? Because it's trans? Yes. E. This is your E1 product. Trans is always better than cis unless it's not. And what do I mean by that? Trans is always better than cis unless there's something going on with cis that makes it more stable that needs, hydrogen bonding. Something, I don't know. As a starting point, trans is always more stable. Okay, why over here did we show trans product? It's more stable. Remember when I rotated it? It rotates because rotating is going to happen, and that's what you get. It all leads to the more stable. Okay. Here's another example. If you take this, heat it in water, or you don't even need water. You can just heat that by itself. It'll eliminate. I showed water. I showed water acting as a base, and the leaving group just left. What's the product? Well, you could eliminate here and put double bond there, but that would only be a monosubstituted alkene. If you put double bond here, that would be a tri-substituted. That would be better. And something has happened here. Maybe nothing happened, but it shouldn't say this. Why is that no good? This alkene does not have E or Z, does it? No. There's no stereochemistry for that alkene. There's your product. I don't know why I put that. Unless I used to have another carbon here, and I removed it. But as shown, that doesn't have any stereoisomers, right? There's no E or Z for that. Tri-substituted. Because we're doing E1. How do we know we're doing E1? Weak base. Weak base or no base? Water is not a strong base, is it? E1. So now that you know it's E1, you can envision the mechanism, ionization, and then the water takes an H and a fast step to put the double bond in. Summary. We've already kind of summarized. E1 always gives the most stable alkene as the major product. What about E2? With E2, it's not going to be as easy. It's going to vary. It depends on base used and orientation of groups in the starting material. Let's look at some examples of this. Does everybody agree E1 should be easy? E1 gives the most stable alkene. Bam. E2. Here's an E2. You take this with hydroxide, a strong base, bully base. Here I come. I want to be involved in the rate determining step. Bimolecular now. I showed beta hydrogens here. You've got this beta hydrogen, and you've also got this. Of course, there's 3 there, but I'm just showing 1. If the base takes this one, and electrons move in, you kick that off, all concerted. That gives this alkene plus the leaving group plus water, protonated base. This is the thermodynamic product because it's the most substituted. If we had removed that H, double bond here, that would be only mono-substituted. So this is the Zaitsev product. Right?
Could you say that the strong base always take the most acidic H as well?
No, I'm not saying that's acidic. None of these H's are acidic.
Not with the rich friends and all?
No, the rich friends would actually make it less acidic. Because we're making anion. But we're not making anions. Remember I showed you making anions? We're not going to make anions here. Also, I'm going to show you something else down here, and then we're going to compare. But right now, it could take that H. If it did take that H, we would get the Zaitsev product. Another name for the thermodynamic product, Zaitsev product? The Zaitsev product is easily formed with an unhindered strong base. That's an unhindered strong base, which has no problem abstracting the more hindered beta hydrogen. Which beta hydrogen is more sterically hindered or crowded? A or B? Which one should be more difficult to reach or get to? A. A is more sterically hindered or crowded. But an unhindered base has no problem abstracting the more hindered beta hydrogen. Because hydroxide is small, it has no problem taking this H, which is in here amongst all these other H's from the methyls. Okay, you see how it's hindered? And we can get the more substituted alkene. In contrast, if we use a bulky base, is the bulky base going to have more difficulty in abstracting this buried H that's in between these methyls? Do you expect it to have more difficulty? It's got wings on it, okay? This is an airplane with wings. Is it going to have more difficulty getting into this hangar with these big old wings on it? Yes. The more bulky your base, the more prone it is to take the more or the less hindered, more accessible H. But if you take that one, you're putting double bond in down here, and you get not the Zaitsev product, not the thermodynamic product. What's the name for this product? It is the kinetic product. Kinetic means rate. This is going to take this H faster because it can get to it quicker. So that's why this is sometimes called the kinetic product. It's not the thermodynamic product, that's the thermodynamic product. What's a name for this? Not Zaitsev, but Hoffman. Hoffman is the kinetic product or the less substituted alkene. This is Hoffman. Hoffman is spelled with one F and two N's. And this is Seitze. I have no idea how to spell Seitze. This product is more likely when using a sterically hindered strong base. Remember, we're doing E2, and the base is involved in the rate determining step of an E2. So the characteristics of the base become important here. Okay, also for E2 we have stereochemical requirements. In an E2 elimination, the leaving group and the beta hydrogen that's being extracted must be coplanar. With anti-coplanar, sometimes called anti-periplanar, very much preferred over syn-coplanar. This is what I mean by anti-coplanar. Remember the Newman, circle, circle, dot, dot? One carbon, another carbon. If we look down the carbons, this is the front carbon. So on the front carbon, the BR is straight up. If I'm looking down here, let's see, no. BR is on the front carbon, so I'd be over here. If I'm looking through there, front carbon, the BR is straight up. And in the back carbon, the H is straight down. Does that look, remember that type of thing? Does everybody agree that this is the view? Remember the Newman? Well, the beta hydrogen and the bromine are anti-coplanar. They're anti, but they're also coplanar. See, they're in this plane right there. Here's a plane. Hey, see that plane right there? They're sitting in that plane. That's an example of anti-coplanar. Both of these. This would be syn-coplanar. They're both in the plane of the board. Now if I drew this like that BR there and this H like this, both of these are coplanar. Is this coplanar? No. The BR is in the board being the plane here. Is the H straight up on the board? No, the H is like this. So this is not coplanar at all. This is anti-coplanar, this is syn. Either one will actually work for the elimination, but which one is most preferred? Anti-coplanar is heavily preferred. Here's why. The base, which has a long pair, takes the H. What do these electrons do during the E2 elimination? They move in here to make pi bond. But look how they're moving in if they're anti-coplanar. They're moving in sort of like backside, and off goes the leaving group. These come in sort of backside. And you're able, this comes in backside when it's anti-coplanar. And there's more to the backside than we've ever discussed. And I'll remind you of, remember when we drew these hybrid orbitals during week 1 and I said there's that back lobe that I drew, but I said I'd never draw it again? Everybody remember that? You don't remember when I drew the orbital like this and there was that little tiny back lobe and I said we'd never draw it again? That back lobe is what things are pumping into when we do backside. And it gets into molecular orbitals and antibonding orbitals, and this causes this bond to break when you pump into that back lobe. That's why when we do backside, that's important there. But it's also kind of relevant here. This comes into this back lobe. So anticoplanar. Now when we start doing examples, we'll do Newmans, but we also are going to go back and consider share conformations. Here's a leaving group. There's a beta carbon with an H, so this is a beta hydrogen. You see how these are anticoplanar. The Br is straight up, the H is straight down. Anticoplanar. Look over here, don't read this. Here's the leaving group. There's one beta hydrogen, here's another. Let's look at these. Are these anticoplanar? They are not. Anti would, this H would need to be like this to be anti. It's not. Also, this is in the plane, but this H is really coming out at you if you know the projections really. Really look at a model. But here's the take home. The only way for an H, a beta hydrogen in the leaving group to be anticoplanar in a chair conformation, the leaving group must be axial. Axial. When the leaving group is axial, one of these H's is straight down, it's straight up. If the leaving group is equatorial, none of the H's will ever be anticoplanar. So here's another take home. When these eliminate, the leaving group always must be axial. Only when it's axial will the beta hydrogen be anticoplanar. I'm setting the stage for the examples we're fixing to see. You thought we could learn Newmans and forget about it, right? You thought we could learn chair conformations and forget about it. By the way, if you're going to take Organic 2, you have to know Organic 1, so don't forget about it. Let's look at this stuff. Show the expected product from this reaction. I'm going to have to help you with the first one. All right, let's step back here. Final exam. We know SN1, SN2, E1, E2. Is this SN1, SN2, E1, or E2? What is it? How do you assess the reaction? I see a strong base / nucleophile. Strong hydroxide, right? So what can we eliminate right there? You can eliminate SN1 and E1. Strong base / nucleophile. It's a bully. It's going to stick its nose in there and be involved in the rate determining step. It's going to be bimolecular. So, is this SN2 or E2? Elena? SN2 or E2? Repeat after me. You do not do SN2 on a tertiary halide. Have we ever said that?
Yes.
So, what is this mechanism? E2. There you go. That's how you have to assess reactions, things like that. Everybody knows you don't do SN2 on tertiary halide, right? E2. Okay, now that it's E2, what are we going to be doing here? I could ask you a question like this. I could say, show all theoretical elimination products. Like we did on that page before where there was 3. let's see, E2, going to give an alkene. Does it always give the most substituted? No. E1 always gives the most substituted. E2 has a stereochemical requirement. How many different types of beta hydrogens in this molecule? Can you identify the beta hydrogens? Where are they at?
Yes.
There's one here. Ah, stereochemistry. What's its stereochemistry?
Which is coming back.
It's back, right? Because that's forward. That's A. Is there another beta hydrogen?
Yes.
Yes,
Where?
yes, right here.
Right here? Where? Move my finger. Right, left?
Right.
Right,
Right there?
Yes.
now.
Left.
Right there? Yeah? Yeah. There's actually 3 there. But that's out. We can put double bond in right here. Don't forget about there. Okay? Show all possible products coming from eliminating. I'm just going to draw one of these as HB. Show all possible alkenes. Just plain possible. No considerations of anything. From beta elimination. How many possibilities to consider? What if we beta eliminate HB? What will the product look like? Somebody have it? If we eliminate HB and of course the leaving group, is that the product? Would we put double bond in right here? Get rid of that. I can't erase the bromine, but would we put double bond in there and then have these 2 things off the double bond? Can I see that, Asian? Yeah, that should be it. What if we eliminate HA? Does someone have that product? What would that look like? We would have, okay, I've got that bond there. That'll become a double bond. I'll have a methyl and an ethyl. But see, that's now planar. So I'm not going to show that with any bold, okay? Because it's now planar. And over here, what's on this carbon? A methyl and a T-butyl. That's from eliminating HA. But, hold on. This has a stereoisomer, doesn't it? I'm going to draw it on the right because I'm out of room. Here, the ethyl and the T-butyl are trans, but we could also draw that same with the ethyl and the T-butyl cis. Eliminate HA. These are stereoisomers, and this is a different regioisomer. Everybody see what I did there? That's 3 very theoretical possible beta elimination products where we eliminated the beta H and the leaving group to put in the alkene. Easy question. If this was E1, which would be formed? If it was E1.
Plus
Yes, big groups trans?
yeah.
Yes, this is your E1 product. Also known as what? Sate-Sev product? That's your E1 Sate-Sev product. But guess what? We're not doing E1. We're doing E2. So which is the product? Well, it varies. Two things. First off, is the base sterically hindered or is it very non-hindered? Non-hindered base. Now we would like to form the more stable product if we can. And hydroxide should have no problem doing that. It's not bulky. It'll be able to get this H. These are more accessible. This one's kind of hidden there on this more substituted carbon. What was it, HA? But are we going to get this or this? The A and the BR need to be what when the elimination takes place? Anticoplanar. Draw on a Newman. Rotate to make HA and the leaving group anticoplanar. Then you will eliminate. We're out of time. You're going to have to do that on your own. We'll look at that first thing next time. Please do this. If you draw the Newman and the leaving group is like this and the H is like this, you need to rotate to make the H anticoplanar.